In this video, we're going to talk about some more examples of probability, in particular, now that we kind of understand independent and mutually exclusive events. So we are looking at flipping two fair coins, fair meaning that they're equally likely outcome of heads and tails. And since there's two of them, that means that we have two possibilities every single time. So let me go ahead and list the sample space really quick for this. We are looking at maybe we get two heads. Maybe one heads, one's tails, and the reverse of that could possibly be true, and tails, tails. Okay, so those would be the possible outcomes. So A is the event of getting at most one tail. So that phrase at most means that you could have one tail, but you could possibly not. You could have less than that. In other words, zero tails. So the outcomes that would qualify would be heads, 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 tails, and tails, heads. Those would all work for getting at most one tail. And then the probability of A is going to be 3 out of 4 or 0.75 or 75%. So part B, they want us to find the event of getting all tails. Well, that happens to be the complement of A. And here, I'm actually going to make a note of that. I'm going to write A prime is the same thing as B, which happens to be two tails, because it's the only thing in the sample space left that isn't in our set A from part A. So that means that the probabilities of both of these are supposed to add up to 1. So I could calculate B by simply subtracting the probability I got in part A, which would be 1/4 or 0.25. It's also very easy to directly calculate B because I'm like, all right, well, there's one event in B out of 4 total. But this method that I'm showing you here is kind of an important method. And we want to kind of start thinking about maybe little shortcuts that might make our life easier. And this is one of them. So I wanted to kind of point out that we could think of this as a complement, and that has some use. Okay, so let's look at the next one. C is the event of getting all heads. Okay, so C doesn't have a connection to A because it happens to be um, something that is in A. But again, it's only one outcome. And therefore, the probability of C is 1 out of 4 or 0.25 or 25%. But on part D, the event of getting more than one tail, okay, more than one tail, that would be, let's see. Well, if it's getting more than one tail, that sounds like it has to be two tails. So actually, D is the same thing as B. Interesting, right? The way it's worded. So B is worded that you get all tails, and since we're talking about these two outcomes, and then D also works for that, getting more than one tail. So D and B are actually equivalent in that sense, though the wording was different. So it would be 1/4 or 0.25. Okay, so E, the event of getting head on the first toss. Okay, so here, let me zoom out a little so I can see my sample space. So getting heads on the first toss. So actually, the very first two I've listed work for that because in both, in my sample space, because both of those events here, we have heads in the first spot, and then the second spot, it really doesn't matter. So E would be heads, heads, and heads, tails. So the probability of E would be 2 out of 4, which will reduce to 1/2 or 0.5 or 50%. The probability of getting at least one tail in two flips. I find it funny that they actually specified one or two because again, they're trying to get us to understand this terminology, at least one. So at least one means that we are going to have at least one tail, but we could possibly have two. That would qualify for this event. So they didn't give us a label for this one. At least one tail, possibly two. So let's see, that would be heads, tails, tails, heads, and tails, tails would all work for that one. Oh, okay. This is the complement of C. This is the complement of C. I'm just seeing that. Yeah, just seeing that. Okay, so it's everything not in C. So if I wanted to, I could just subtract what the probability of C was, and that would give me from 1, and that would give me, let's see, 1/4. Okay, so 3/4 or 0.75. I don't have room to put that in, so we'll just put it in fraction form. Okay, let's look at another example here. So let the event C be taking an English class and D a speech class. Now they give us the probability of C and the probability of D and the probability that somebody would take an English class given that they are taking a speech class. And then the probability that somebody is taking both a speech class and an English class. So they're asking us, are these events independent? And we have a way of checking for independent. The way we check for independent, let me go ahead and do it in green, is that if the probability of a given, oops, that should have been a C, equals the probability of just the event happening. In other words, the event D doesn't affect whether or not C happens. Okay, so basically we're asking, are these two things equal? And the answer is no, it's not. Because, oh wait, no, I'm sorry, it is. Oh, look at that. Sorry, I looked at the wrong one. I was looking at probability of D. So 0.75 equaling 0.75, they are equal. So yes, they are. Those little 3 dots there, that's like a science notation for conclusion. We see it a lot in statistics. So just so you know, are they mutually exclusive? So mutually exclusive, we had a little way of checking for that. That means that both events can't happen at the same time. So this probability, both of them happening, would be 0. And that's not the case in this one. So because the probability of C and D does not equal 0, then no, they are not mutually exclusive. There are people who take both speech and English at the same time. Okay, now they want to know, what is the probability of D given C? So for this, we're going to use a little bit of a formula for that. And the formula we'll be using is, it is the probability that D and C both happen, which is the same thing as if I said C and D, over the probability of C. So this means that we're looking for all of the things that D and C have in common over just C, okay? Like all the events that are happening with C, because we're limiting ourselves to only looking at C when we're doing a given like this. Okay, so probability of D and C, or which is they gave us a C and D, same difference, is 0.225. Probability of C is 0.75. So if we divide that, it looks like I'm going to get 0.3. So those are kind of little problems that help us use some little like formula checks to kind of answer those questions. All right, so let's look at this last example here. In a particular class, 60% of the students are female. 50% of all the students in the class have long hair. 45% are female and have long hair. Of the female students, 75% have long hair. Let F be female, let L be long hair. Okay, wow. So a lot of information. Let's label what they have given us here, okay, with their labels. So F being female, L being long hair. So the first thing they tell us, 60% of the students are female in this class. So that would be that the probability of being a female is, wow, let's fix that. There we go, is 0.6. I'll go ahead and, convert it to decimal form. 50% of all the students have long hair. Okay, so now they've given me the probability of having long hair. So that's 50%. 45% are female and have long hair. Okay, so that would be the probability of F and L, and that's 54%. Of the female students, 75% have long hair. Now, that is a condition. So they're talking about only looking at the female students. Of those female students, how many of them have long hair? That is this condition. So we're looking for the probability that they have long hair, given that we're looking only at the female students. So that is 0.75. So they want to know, are the events being female and having long hair independent? So we had a way of checking. We can use the condition and say that if this equals this, if the given equals the same thing as finding just the probability of long hair, okay, then they're independent. And looking at this, let's see, we have 0.75 equal to 0.5. Okay, so no. So no, they're not. There is another way of checking this. I just want to bring up really quick. The other formula we can use is the probability of L and F if it equals the probability of L times the probability of F. That was one of those three formulas we listed when we talked about independence in the previous video. So we could check this too. And the reason I'm bringing it up is maybe they don't give us the conditional. Maybe they give us the other pieces of information. So this is how we would check. So we would do 0.6 times 0.5. And that's going to come out to 0.3, which again is not equal, which I knew. All right. So no, they are not independent. They do depend on each other. Being a female does affect whether or not somebody has long hair in this class.